Hi all, welcome back to another lecture of DBMS, and in this lecture we will learn about inference rules. Then we will see what is chase and backchase algorithms. After that we will learn about equivalence of functional dependencies, and then we'll see what is minimal basis, what basically canonical cover. Then we will see the definitions of dependency preservation and lossless decomposition. So stay tuned for the video, and let's start with the very first topic, which is inference rules. So inference rule, in the last lecture, we have already learned about 7 different types of rules. With the help of what we can find out the new functional dependencies from the given functional dependencies, right? So that is what these are the logical rules used to derive new functional dependency from a given set of dependencies. And it is important in data normalization. So if we have the left part is called data determinant, we know, and y part is called dependent. So functional dependency from x to y, it says that y is functionally dependent on x. So suppose we have a IRCTC system, we have a train table, and here we say that train ID says defines date, right? So we have a date column here and a passenger column here. So train ID defines date and date defines passenger, right? So x defines y and y defines z. So we have one rule called transitivity. From this, both of these functional dependency, we can derive x defines z, right? So this is what different types of rules. Out of those, with the help of transitivity rule, we can say that if x defines y and y defines z, x also defines z. So here train ID defines date and date defines passenger. So we can say train ID directly defines passenger, meaning the train ID can determine passenger indirectly. So these are the different inference rule, and about 7 different types of inference rule we have already learned in our back-to-back lecture. So if you have missed it out, so I will request you to go and check that video and learn these things, then come up to this video. Second is chase and backchase algorithm. So chase algorithm is basically used to test if a given set of functional dependency holds in database schema or not. So if we said that x determines y, this is a functional dependency. So chase algorithm says that you need to check in this table that for every x, let's suppose, which is train ID, determines, let's suppose, train name. So for every x determines y, it says true or not. Like for 101 is like for with the train ID 101, it means always a train name will be Rajdhani only. Is it true for every row or not? If it is so, then basically we are checking this and confirming it by chase algorithm. But in case of backchase algorithm, it is totally opposite to the chase algorithm, and this is basically focusing on the query optimization. It reverses a chase process to find a minimal representation. So in this case, instead of validating that the functional dependencies are holding true or not in the table, we are focusing on the minimizing the representation of the functional dependency and optimizing the database query to basically check the minimal redundancy, that the duplicate should be less. Along with that, minimizing the number of functional dependencies, right? So let's suppose in the IRCTC table, we can verify the functional dependencies like train ID defines date. So here we can say that train ID defines date. Like for 101 ID, we have same date, right? So we can say that this functional dependency holds true value in the bookings table. So we can say this is because of chasing algorithm, right? Now let's move on to the equivalence of functional dependency. So what is equivalence of functional dependencies? When two set of functional dependencies are given, right? So we try to find out the closure of both the functional dependency. If somehow the first set and second set matches their closure, then we can say both are equivalence. Let's see how. So basically, let's suppose in the first set, we can say train ID determines date. And in second table, it says train ID determines passenger and passenger determines date. So in the second set, with the transitivity rule, we can say train ID determines date, right? Date. So this functional dependency of set D and this functional dependency of set A are both same. So now we can say these two sets of functional dependencies are equivalence. So that is what the definition of it says. The two sets of functional dependency are considered to be equivalent if they imply the same functional dependencies. To check the equivalence, we first compute the closure of each set. So we will find out the closure of each set. Closure is nothing but the set of all functional dependencies. Find out the new functional dependency or the older one, and then we'll match every functional dependency exists in both the sets or not. If it matches, then the both set of functional dependencies are equivalence, right? So here train ID determines date and train ID determines passenger. So with the inference rule of transitivity, we can say that train ID directly determines date, okay, which is already there in the set A. So we can say these two functional dependencies set are equivalent. Now next is what is minimal basis, that is canonical cover. So it is a simplified set of functional dependencies where all redundancy have been removed and all dependency are in the simplest form. So this basically focuses on removing the redundancy, and as well as it also focuses on minimizing the number of functional dependencies or the complexity of functional dependencies. So let's suppose if we are saying A determines B and C together, and if you are feeling that determining B and C together with the A is more complex, then you can minimize it saying A determines B and A determines C. So you have minimized the functional dependency in the simplest form to understand and to find the relation between the tables. That is called minimal basis or canonical cover. These steps reduce the complexity in database normalization. So let's see in the IRCTC table, if we have the functional dependencies like train ID determines date and passenger, and date determines passenger. So we can say after decomposing that train ID determines date and train ID determines passenger. So this individually and this individually. So here we have simplified it. Now we have from this train ID determines passenger and train ID determines date. We can say date determines passenger. So here we have simplified. Here we have found out the new dependency to in the more simplest form to find the relation basically for in the normalization case. So this is what minimal basis says. It focuses on removing the redundancy, basically the data duplicacy, and also it focuses on minimizing the functional dependency complexity, right? Now next topic is dependency preservance, and it is very much important. And in the interviews also they mostly ask this type of questions, and so having the proper understanding is very much important. So let's try to understand this topic with few examples also. So dependency preservation means it says when you are with some rules, when you are breaking the functional dependencies into smaller ones, or if you are combining those smaller functional dependencies to find a meaningful relationship, if you are doing so now, that none of the single relation of the functional dependency should miss. So that is what it says, the dependency should be preserved. So it refers to the ability to maintain all functional dependency when decomposing a relation into smaller relations as a part of normalization. So when you are decomposing, basically breaking the relationship into the smaller ones, the all dependency should be preserved. Like if you are saying A determines B, C, D, and you have divided into smaller things like A determines B and A determines C, and if you missed that A also determines D, right? So you have found out only these two. So in future, if you will combine it, you can only find out A determines B, C, right? So where that D goes, you miss that one dependency, right? So it should not be the case. If you are dividing that complex functional dependency or decomposing it into simpler forms, every dependency should be preserved. So let's take the example. So if you have train ID, passenger and date, one table, and if you're dividing it into two tables, one table having R1 having train ID, R1 having train ID and date, okay, and another table you have divided where you are saving date and passenger, okay, date and passenger. So here you can say train ID determines date, yes, and date determines passenger. Okay, and these were the only dependencies in the larger table also, and in smaller tables also the dependencies are preserved. So here you can say the dependencies are preserved and none of the dependencies are missed. So basically what it says, before dividing the table into smaller ones or before dividing the functional dependencies into the smaller functional dependencies, whatever the number of functional dependencies was there in the larger table, after dividing it also the functional dependencies are same or not. Right, the relations are same or not. You can derive every relation in the smaller ones also or not. If it is so, then you can say dependencies are preserved. If not, then dependencies are not preserved. Okay. Now next is lossless decomposition. So it is also similar to dependency preservation. Here we talk about we should not miss any attribute or column when we are dividing the larger table into the smaller tables. How? It ensures that no information is lost when a relation is decomposed into the smaller relations. So let's see how we are how we might lose the information. So let's see, we have a table where we have booking ID, train ID, passenger, and date. So we have 4 attributes here, and you have divided the larger table into smaller ones. So where in R1 you are saying train ID and date is there, okay, and in R2 is you are saying passenger and date is there, passenger and date is there, okay. Now but you can see booking ID is not mentioned in any of the table, right? So if you have some relation of booking ID with some other attribute in the larger table, but in smaller tables, as you do not have this column in your smaller table, so basically you don't have the relation with the booking ID as well. So you missed the functional dependency here, right? So in this case, you can say the dependency is not preserved, one thing, and second, you missed the one information as also you have missed that attribute. So when in future you will combine those two tables back, you can never get that booking ID back, right? So here you have lost the decomposition. That will be called lossy. This is the case of lossy decomposition. So basically you have lost it, right? So to maintain it, what you can do, you can create another table R3, and here you can mention booking ID or another one more attribute, either train ID or passenger, right? So basically any of the ID. So basically you will be creating 3 table to maintain that, so that in future if you are combining or joining those smaller tables back to retrieve the data, then none of the attributes should miss. So that is about lossless decomposition, how you can find out how you can opt for lossless decomposition in this case. So that is it about the whole lecture. I hope you learned. Now let's meet in another lecture. Till then, keep learning and take care of yourself and your family too.